This is going to be 11.3, the integral test and p-series. So far we've been talking about a couple of tests on how to be able to figure out whether a series is going to converge. So if you have some sort of series, n goes from 1 to infinity, of a sub n, we are interested in whether this is going to be convergent, so it converges, or whether it diverges. That's what we're really doing. And right now, we've only looked at one different thing, which is basically the test for divergence. This is the first thing that we kind of talked about. So the test for divergence basically means that if the limit as n goes to infinity of a sub n is not equal to 0 or does not exist, then what happens is that the sum from n goes from 1 to infinity of this a sub n diverges. That's basically what the divergence test says. So we also talked about geometric series, harmonic series, and telescoping series. So telescoping, geometric, and harmonic. And we kind of figured out a couple of things. You can look at the videos that I posted before this one to kind of take a look at those three. And mainly the one that you really wanted to figure out was the geometric one. And we said that if the common ratio was less than 1, we can figure out the sum of all of these guys by using this formula. And if it was less than 1, then we knew that you had a convergent series. So the thing about this is that if I were to give you some other type of series, it's going to be a little harder to figure out its partial sums. So the reason why telescoping, geometric, and harmonic were nice were because they have a particular form, but not all series have the same exact form. So finding a formula for partial sums is tough. Okay, so generally it is really, really difficult to find a formula. So what we need to figure out is that the test for divergence is a very general test that can help us figure out whether something's diverges or converges, or well, just diverges. This one is more specific. It kind of tells you whether it converges or diverges, and then it gives you the sum. So we need to have some other general tests that are going to be that we have under our arsenal to be able to figure out, we know this series is going to converge. We don't know to what, but we know that it can. So for example, let's say we wanted to find the sum from n goes from 1 to infinity of 1 over n squared. Okay, so one of the things that we can do is that we can go ahead and expand this. So it'll be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on and so forth. Okay, so the best way to really do this is by using a computer. So using some sort of computer table, we are able to approximate what the sum is. So now another thing that we're going to try to do though is, well, why don't I just try to figure out, since we're basically adding stuff in calculus, when we're adding different things, we're basically finding the integral of it. So if you were to kind of look at the equation of 1 over n squared, and what we were to do is make really, really small rectangles like Riemann sums, like how we did before, and all the way until we get to infinity, well, all we're basically are doing is taking the sum of the rectangles, okay, adding them all together, and basically adding the rectangles is just basically giving us a integral. So this is what we're going to call, so we have a third thing. So we had the first one, which was a divergence test, the test for divergence. The second one was whether a series was telescoping, geometric, or harmonic. This third one is what we're going to call the integral test. So this is the next test under our arsenal. So integral test. Okay, and basically this is what it says. So this is what the integral test says. So suppose f is continuous, positive, decreasing function. on the interval from 1 to infinity. Okay, and let a sub n equal a function that has n in it. Okay, then the series, the sum from n goes from 1 to infinity of a sub n is convergent. Okay, so it is convergent if and only if the improper integral okay, so the integral 1 to infinity of f of x dx is convergent. Okay, so basically, if I wanted to kind of have it in different bullets, this is what we're saying. If the integral from 1 to infinity of f of x dx is convergent, then summation from n goes from 1 to infinity of a sub n is convergent. Okay, so if the integral converges, so does the sum. And also, if the integral from 1 to infinity of f of x dx is divergent, okay, so if it diverges, then the sum from n goes from 1 to infinity of a sub n is also divergent. Okay, so here are a couple things. So this is what the integral test does. So all I got to do is take the integral of the function within x, take the integral of it, and then if it goes to a number, it's convergent. If it doesn't, then it's divergent. Okay, now also just to look at a quick little note, even though I have a 1 here, a 1, that doesn't necessarily mean that it has to be a 1. So it does not need to be a 1. It doesn't need to start at 1. It can start at 5. It doesn't really matter. Okay, so that's basically what it says. Now notice that there's a couple things that you have to really be careful with. We need to make sure that the function is continuous, which for the most part is good. It has to be positive so it doesn't go below the x-axis, and it also has to be decreasing. Okay, now if you forgot how to figure out whether something's decreasing, please go ahead and check it out. Another way that you can figure out whether it's decreasing is you can take the first derivative and see that it's actually negative. So if it's negative on that on its particular domain, then you know it's going to be decreasing. Okay, so now let's go ahead and try to use the integral test on a couple problems. So here's an example. Okay, determine if the series is convergent or divergent. Okay, and here's my first problem. So the summation from n goes from 1 to infinity of 1 over n squared. Okay, so we're going to try to figure out whether this thing is going to be convergent or divergent. So the first thing that you want to do, you can try to do the test for divergence. And actually, let's go ahead and do it. Let's see if the divergence test works. Okay, so notice that we have to take the limit as n goes to infinity of 1 over n squared. Well, this is just going to give me 1 over infinity, which is going to give me 0. So this doesn't give me any information at all. So I still don't know. So the test for divergence didn't really help. Okay, so now what instead I want to do is, since this one did not work, I need to do some other tests. So now let me try the integral test. Okay, so the integral test says first that I have to make sure that it is continuous, positive, and decreasing. Okay, so if you know what 1 over n squared looks like, it kind of looks like this. Okay, this is what 1 over n squared looks like, and remember that you're starting at 1 all the way to infinity. One way to also check that it's decreasing, if you don't remember what the graph looks like, we know that f of x is going to be 1 over x squared, okay, which is also x to the negative 2. If I take the first derivative, okay, I'm going to have negative 2 x to the negative 3 which is negative 2 over x cubed. If I were to plug in any value of x that's greater than 1, you see that this function is always going to be negative, so that means it's always going to be decreasing. Okay, so that's another quick way to kind of figure that out. Okay, why that's going to be decreasing. Sometimes if the function is really, really difficult, it'll be really hard to take the derivative, so you might want to do something else. Okay, so we know that it satisfies the assumptions. So all I have to do is, in order for me to figure out whether this is going to be convergent or divergent, I just have to take the integral from 1 to infinity, right, because it starts at 1, of 1 over x squared dx. Okay, which is basically 1 over n squared, but I'm plugging in an x. Okay, so this is going to be the integral from 1 to infinity of x to the negative 2 dx. Let me substitute that infinity with something else. So I'm going to write the limit as, let's say, b goes to infinity from integral from 1 to b of x to the negative 2 dx. So this is going to give me the limit as b goes to infinity of x to the, if I add a 1, I'm going to have x to the negative 1 divided by negative 1 from 1 to b. Okay, and now what I'm going to have is the limit as b goes to infinity of negative 1 over x from 1 to b. And then let me plug it in. Limit as b goes to infinity of negative 1 over b minus negative 1. So this gives me the limit as b goes to infinity of negative 1 over b plus 1. Now all I have to do is plug in the infinity. Okay, so I'm going to plug in the infinity here. So this is just going to go to 0. So all I'm left with is just 1. I'm going to be left with a 1. Okay, so what does it say? Well, the improper integral, the integral from 1 to infinity of 1 over x squared dx, converges. So by integral test, what does that tell me? The summation from from n goes to 1 to infinity of 1 over n squared also converges. Okay, that's the answer. Now, the answer to this summation is not going to be 1. Okay, the answer is not 1. Okay, it's something else. But this just helps us figure out that if this converges, then this also should converge as well. Okay, but this doesn't necessarily mean that that's going to be the sum. You have to use some sort of computer algebra to try to figure that out. Okay, but that's just basically what it is. Let's do one more problem. Okay, so let's do this problem. Okay, so let's say we want to figure out f of x. Well, not f of x, whoops. Summation from n goes from 2 to infinity of 1 over n ln of n. Okay, so first, let's just go ahead and just jump into the integral test. Because if you see, if you do the test for divergence, you're going to get another 0. So we're going to use the integral test. So integral test. Okay, so what we're going to do, we're going to take the integral from 2, because this now starts at 2, all the way to infinity, 1 over, let's substitute the n's with x's, x ln of x dx. Okay. So now all I have to do is just try to evaluate this integral. Let's get rid of that infinity. So let's write the limit as b goes to infinity, the integral from 2 to b of 1 over x ln of x dx. Okay, here what you want to do, let's go ahead and do u substitution. So I'm going to have u is equal to ln of x, du is going to be equal to 1 over x dx. Okay, so you see that the derivative itself is right here. Okay, so this is going to be equal to the limit as b goes to infinity of the integral from 2 to b, and these are for x's. 1 over x is just going to be du, so I'm going to have 1 over ln of x, which is going to be u, and then this is going to be du. Okay, So this is going to be equal to the limit as b goes to infinity of this is going to be just the ln of the absolute value of u between 2 and b in terms of x's. Now let me just plug in what u was. I'm going to get the limit as b goes to infinity of ln of x is going to be between 2 and b. And now all we have to do is just plug them in. Limit as b goes to infinity of ln of b minus ln of 2. Okay? Now, if I were to put the infinity here, this guy's just going to be infinity. And this whole thing is also going to be infinity minus some number that's going to give me still infinity. So this thing, this improper integral, diverges. So integral from 2 to infinity of 1 over x ln of x dx diverges. So the summation from n goes from 2 to infinity of 1 over n ln of n also diverges. Okay. Okay, and that's the answer. Now, one of the things that I didn't check was that this is actually decreasing. You can probably try to figure that out, that it's actually going to be decreasing. You can kind of look at it. If you can't quite, because n and ln of n are both functions that increase continuously, this is just going to be and since I'm doing 1 divided by something, it's going to be continuously decreasing. But you can either take the derivative or you can do it the way that we did it before to show that that's actually going to be decreasing. So if a problem also tells you the function is decreasing, then you don't need to really check anything because it already told you.